We're going to talk about hypothesis testing, specifically testing a mean. Our primary question is to determine if a result that we got is significantly different or unusual compared to what we expected. Let's go ahead and go through this first example. So a national report states that the average amount spent on textbooks for a four-year degree is $3,262. The Student Senate feels that seniors they know have spent way more than this. They conduct a study of 50 randomly selected seniors and find that the average debt or amount spent on textbooks is $3,728 with a standard deviation of $997. With alpha equal 0.05, is the Student Senate correct? Okay, so there's a lot of information there. So I want to first talk about this notion of, are we getting something that was unexpected to compare to what we did expect? So what we're expecting is what the report is. I know that we've said, gosh, we think that this is bigger, but if we go based on this national average, then that really should be the amount expected. Sort of innocent until proven guilty. So we're going to assume that it really is $3,262. So this average debt for textbooks turns out to be higher than that, $3,728. We want to know, is this amount higher because just some quarters you spend more than other quarters, or is this unusually higher? So this is our sample result. We've talked about the normal curve, and we know what an unusual result might be. So if I draw a normal curve in here, we've got the expected value here at 0. This is going to be our 3262. That's my expected value based on the national average. We could be, if I just label this with standard scores, I could be 1, 2, or 3 standard deviations away. So -1, -2, -3, 1, 2, and 3. If I was 1 standard deviation away, I would expect it would be 68% of any sample, any random sample of 50 seniors to fall within 1 standard deviation. I would expect within 2 standard deviations, so it was our 68, 95, 99.7% rule. So within 2 standard deviations, I would expect nearly all, 95%. It would be really unusual to be outside of 3 standard deviations, because within 3 standard deviations, I'm going to write my number over here because I'm out of room, that would be 99.7%. So when we talk about something being really unusual or very unexpected, it means that we're landing over here somewhere, either 2 standard deviations away, or even better, I'm actually way over here at 3 standard deviations away. So I'm in just that 0.3%, or if I'm in the purple, I'm in that 5%. So when I take a look at this alpha equals 0.05, which is this right here, we call this our significance level. Let me get my regular pen back. This is my significance level. How significant or how unusual do I want this to be? So my significance level is 5%. So I want to be just in the 5% area. So we would be talking about 2 standard deviations. We can split this 5% between the 2 tails like we see here in the normal curve. We could even put all the 5% into a single tail, either all 5 on the left or all 5 on the right. So what we're saying is we want to be unusual enough that we're in only the 5% group that is different enough from 3262. There's going to be a lot of different averages, but we want our average to be so unique that it falls into a group of only 5% of samples of 50 students. Okay, so that's our significance level. So there's a lot of vocabulary here. We talked a little bit about the expected value. The expected value is our null hypothesis, and we label that with an H sub 0. when we put a null hypothesis together, we do it with a parameter, with a statistic, which would be, when we put a null hypothesis together, we do that with mu. We do that with one of our parameters or Greek letters to denote that this is our expected value, not our sample value. So this is going to be our 3262. Whoops, 3262. Okay, so 3262. Alternative hypothesis. Typically, this is what our assumption is, or this is kind of what our feeling is. The feeling in this one is that they think seniors have spent more than this. So for this alternative hypothesis, which we label H sub A, or you'll see that as H sub 1, this case, it's going to be, we think it's actually bigger than 3262. Should have made these a little bit bigger. Okay, sample size, that one's easy. N is equal to 50. Sample mean, that's going to be the mean that we found in our sample. We're going to call that X bar. You could also call that lowercase m, 3728. Significance level, that's the area under the normal curve that we want to be in to be able to conclude that we're significantly different. So significance level is alpha. This case is 0.05. My rejection region. So the rejection regions, just to give you a general idea, we'll go through another example here in a minute. But these are the shaded regions. So this is the shaded area. It's not always going to be shaded, I guess. But it's the shaded area in the tail or tails with alpha equal the area. Okay, so that's going to be the tail. 5% is what we're shading here. Z-test versus t-test. I've actually got that written down here down below. So we want to make sure that we're only using the normal curve when the normal curve makes sense. And the normal curve makes sense, or those z values make sense, if we know what the population standard deviation is. We don't always know what the population standard deviation is. Actually, we rarely do. So if we don't have a population standard deviation, then we're going to use a t-test. So if no population standard deviation is given, we're going to go ahead and estimate that normal curve with the t-curve. So we're going to use a t-test. Type 1 error, type 2 error, we're going to talk about those as we move through the examples. Some more to come on the type 1 error. Basically, we want to minimize any possibility of a bias. So type 1 error and type 2 error, we'll talk about those as part of our conclusions, and then also the p-value. We'll talk about that one too as we move through. It's a really nice one to do with the calculator. I want to move on here to example B. In example B, we have a biologist who claims that domestic cats have necks with a mean diameter of 5 centimeters. A random sample of 40 cats reveals a mean of 4.97, close, but a little bit less. And we're given a sample standard deviation of 0.33. Test the claim that the neck diameters are lower than 5, and we're going to test the claim at the 0.01 significance level. As we're going through this, I'm going to go ahead and grab my formula page. So you want to print out, and I'll show you what pages I really want you to print out of the important formulas page. You don't need anything on page 1. We've gone through all of this. A lot of this we have the calculator compute for us. If you want to, you can. But nothing here that you need. I think it's a great idea, though, to print page 2. So we're going to use some of these formulas, but we're actually going to let the calculator do most of the heavy lifting here. You'll notice, so we're going to be doing hypothesis testing right now for Z and T. This Z score is the mean minus the expected mean, so score minus mean. And instead of just dividing by the standard deviation, we're dividing by the standard deviation over the square root of n. This is an averaged standard deviation. What we're really doing is we're comparing a sample mean to several different means from samples of the same size. So we need to adjust our standard deviation. So you'll notice that this is almost a z-score. I've got just this adjustment because we're comparing it to other samples. So divided by the square root of n. But we'll be letting the calculator do a lot of that work for us. But as you scroll down here, you want to print this page too. I think this is the most important page for what we're doing right now because it gives us a procedure table. There's a 5-step process as you're going through the hypothesis tests. This is for the traditional method. They list a 5-step process for the p-value method as well, but I'm actually going to clean that up for you just a little bit because I think that this step is unnecessary. So instead, we're going to do step 1, 2, 3, 4. So we're going to do a slightly shorter p-value method when we get to that. These both end up with the very same conclusion. So whatever your decision and summary are, they'll be the same regardless of what process you used. Okay, so continuing down through what I want you to print, the other thing that you're going to want to print is this really nice table, not table E, that is not a really nice table, table F. So the other thing that you want to print is table F. Table F uses degrees of freedom. Degrees of freedom, df, is n minus 1. So if you think about it, if I know all 9 out of 10 values, then if I have any kind of a measurement like an average or something else, I can always get back to the last value. So we call that degrees of freedom, n minus 1. So just one short of the sample. So using n minus 1, we're able to find our t values. So all of these values in the middle here, these are all t values. But you'll notice as our sample sizes get bigger, our t values get closer and closer to these values, which are the z-scores. And these are the z-scores that line up with areas under the normal curve. So for example, 95%, let's see, so that should be about 2 standard deviations away, right? So 95%, so I'll do it in 2 tails, so I'm 2 standard deviations above, 2 standard deviations below, and I end up with 1.96. So I'm very, very close to the actual z-score. You can see my t's were bigger, and now they're getting a little bit smaller and getting closer and closer to that 1.96. Okay, so these give you the t values, and then at the very bottom you also get those z values. So it's a really, really great table. It's got everything in it that you need. So just those pages for now. So table F, and then the 2 pages from the formulas, the one that has the procedure tables in it, and then the one, if you want, you maybe don't even need this, but the one that has the chapter 8 and chapter 9 things in it. Okay, so we're going to be using that. We're going to go through, we're going to start with this 5-step process. So we're going to start by creating the hypotheses. There are always 2, so there's the null hypothesis and the alternative hypothesis. You're going to see me probably using H sub A and H sub 1 interchangeably, so I'm just warning you at the beginning here that I might use one or the other. They're interchangeable. You want to find the critical value from the appropriate table in Appendix C. This is going to be table F. Compute the test value. This is going to be either using a formula or, even better, the calculator. And then we want to make that decision. Am I really in the unusual area? Am I significantly different enough or not? And then summarizing the results is just writing it all out in English. And you'll notice that with the p-value method, with the exception of finding the p-value, which is the area under the curve that happens to go with whatever your sample mean is, everything else is the same. I've got the same hypotheses, I've got the same decision, and the same summary. So let's go ahead and go back to example B. So in example B, this is the biologist with the cats and the neck diameters. Okay, so kind of a little funky example, but that's okay. We can work through it. So we want to decide what are our sample values and what are the values that we're comparing it to. Here's our sample. So we've got a sample of 40 cats. Let me grab my blue pen and we can write these down. So n is equal to 40. We have a sample mean that's going to be x bar. So x bar is equal to 4.97. Neither of these are part of my hypotheses. a sample standard deviation. We do not have a population standard deviation. No population standard deviation. So we know that we want to use t-scores for this one. So we have a sample standard deviation S of 0.33. Test the claim that the neck diameters are lower than 5 centimeters. So the 5 centimeters must be what we're expecting. So as we put step 1 together, the null hypothesis is what we're expecting, always using a parameter. So in this case, it's mu for the population mean. So we're expecting a mean of 5, and it either is equal to 5. My null hypothesis is always equals. The alternative hypothesis will always have one of my inequalities in it. So it will either have less than, greater than, or not equals. The null will always have equals. The alternative will have one of the 3 inequalities. This time it's lower than. So it's going to be, is the mean actually lower than 5? Okay, so that's step number 1. Step number 2. So if we go back to our procedure table, step number 2 says to find the critical value from the appropriate table. This time it's table F. So I want to find the critical t-score. So I'm going to go back to this table in just a second, but let me set it up for you first. We're looking at a t-curve, but it's very similar to the normal curve. It's going to look like this. My expected value, this is where t would equal 0. My expected value is 5. So those are my actual neck diameters. The value that we have is 4.97. So it lives over here on the left somewhere. I'm not exactly sure where. I'm going to put that in here in a minute. But I know that I only want to allow a 0.01 significance area. So I'm only going to be significantly less than in this 0.01 area. So there it is. It's teeny, teeny, tiny. That is my significance area. This is my rejection region. My rejection region is where I'm very unusual compared to all of the other samples of 40. So my rejection region, and it has size or area of 0.01, and leaving myself, that would be 99%, right? Or 0.99 for the rest of the area, which I'm saying is close enough and not unusual. So 0.99 is my fail to reject area. So fail to reject, just getting that set up a little bit. So what I really want to know is this t value right here. What cuts off 0.01? So to find that value, I'm going to go ahead and start with degrees of freedom. So I'm going to look for that critical value. I'm going to do this on table F. Table F. I do need degrees of freedom. Degrees of freedom is n minus 1, so 40 minus 1, which is 39. I need my significance level. My significance level is 0.01. And I've got a single tail, not split into 2. This guy right here is 2 tails. You'll get used to all of this. So this is a 1-tail test. We need that also to read our graph. Okay, so let's go to table F. Tables. Okay, so as we scroll through here and look for table F, there it is. We have not a confidence interval this time, but we're looking for a 1-tail test, and we have 0.01 as our significance level. Degrees of freedom, let's see, it's right smack in between 38 and 40. So we want to be conservative, so instead of using the larger number, we always use the smaller number. So I'm going to go ahead and use 38 instead. So I know that n minus 1 is 39, but we want to go lower to be conservative, so we're going to choose 38. So if I take 38 and I line this up, I end up with 2.429. That makes sense, right? Between 2 and 3 standard deviations away. So 2.429. Let's go back to our hypothesis test. Okay, so my critical value is 2.429. 2.429. Let me highlight what we've got here that's important. We have our null hypothesis, our alternative hypothesis. This one's the most important because it tells me that I have a tail on the left. I'm less than, which gives me this tail here on the left. And now I've got my critical value. Okay, I'm ready for the next piece. The next piece is to find my test value, step number 3. I really don't know. This is going to be my T4, 4.97. I really don't know where 4.97 lives. I mean, I feel like it's going to live over there, but I really don't know until I figure out what its t-score is. So we're going to use that adjusted value. So t is equal to, it's going to be my sample mean minus the expected mean divided by the adjusted standard deviation. So the standard deviation over the square root of n. This is an averaged standard deviation for all of the different samples of 40 cats that I could have taken. So as I'm calculating this, I get 4.97 minus 5 divided by 0.33 over the square root of n. Let's go ahead and put that into my calculator, which I think is off. So I'm going to do parentheses 4.97 minus 5 divided by parentheses 0.33 over the square root of n, which I didn't write in there, but n is 40. Close parenthesis. This is kind of the moment of truth here. So we get a negative 0.5749. So this is about negative 0.5749. That's something I left off, didn't I? If I get rid of the equals in front of my critical value, that really is a negative because I'm on the left of 0. This is really a negative here. So my value kind of where I expected it to be, right? Let me grab another color pen. This is actually not even close to that critical region. It lives over here somewhere, negative 0.5749. So I'm not significantly different. I would need to be more than 2.5 standard deviations away from that expected value of 5 to say that I was significantly different. I'm going to highlight that guy as well because that was the third important piece. And now I'm ready for step 4. Step 4 is my decision. The decision, there are only 2 options for the decision. I'm either going to reject the null hypothesis. It's all based on my null hypothesis. So I'm either going to reject the null hypothesis or fail to reject the null hypothesis. My sample was actually pretty darn close, and it certainly wasn't more than 2 standard deviations away. So it was pretty darn close to 5. So for my conclusion, I can't reject. So I'm going to fail to reject. So I'm going to fail to reject the null hypothesis. And I just write it like that. Let's highlight that guy too. It's like writing an essay, right? I need all of these pieces to construct a full hypothesis test. And then finally, I need to summarize, and that's answering the question. So test the claim that the neck diameters are lower, and by lower we always mean significantly lower. They were a little bit lower, but not significantly so. That's just, you know, of course it's always going to be different. So that's just a matter of being off because of chance. So step number 5, we do not support the claim that the neck sizes are lower. I'm just going to say that the necks are lower or smaller than 5 centimeters. Okay, so let's go back through. I'm going to highlight this guy too because that's important. So you have to actually say what the heck all of this means. Okay, so as I go back through, that was a sentence there. Okay, so as I go back through, I should see my 5 steps. My first step, these are my hypotheses. So I've got the null hypothesis, which is always the equal sign. I'm going to actually write on this in a different color. So my null hypothesis, always the equal sign. The alternative hypothesis could be less than, greater than, or not equals. In this case, it was a less than symbol. And then I moved on to step number 2, which was to find the critical value. We used table F. And then finally, our test value. So step number 3, to find that test value, we computed the t-score. So we computed. And we did this by taking x bar minus the mean divided by the standard deviation over the square root of n. For that decision, so step number 4 is the decision, there's 2 choices, we either reject h sub 0 or we fail to reject the null hypothesis, always based on the null hypothesis. Think about a trial. So when the jury comes back, they either say we found the person guilty or not guilty. They never say that they're innocent. So it's just a really careful wording kind of a thing. And then finally, step number 5. Step number 5 is just restating the conclusion, but now in English, right? So now you're just kind of explaining what you came up with in words. I do want to show you how to do this one. I'm not going to go back through the whole entire thing, but I do want to show you how to find the test value using the calculator. So we're going to do this step right here. We'll see if I got it right, using the calculator. So I'm going to go ahead and clear this. If you don't have a TI-83 or a TI-84, you're going to want to either borrow one from the library. They do have curbside pickup, but you can also download one for free on your phone. You can also use Wabbit EMU, so a free emulator, which is also free. But you definitely want one for the hypothesis testing. It just makes life so much easier. So I'm going to go to the stat menu and then over to tests. I did a t-test. This should say of the mean, but I did a t-test. So I'm going to arrow down to t-test. I don't have raw data. I did have like a computed mean and standard deviation. So I'll say I had statistics. And then my null hypothesis. Do I already have my values in here? That'd be kind of nice. No, I do not. Okay, so let's see. So this is going to be, I was expecting a mean of 5. My sample mean was 4.97. My sample standard deviation, that was the 0.33. Sample size was 40. And this line right here, this is your alternative hypothesis. Notice how it gives you the 3 choices, not equals, less than, or greater than. We did less than, so we had a single tail on the left. So less than there, and then calculate. Okay, I did amazing. So 0.5749, negative 0.5749. So a really great way to figure out that test value. It also confirms some things. It confirms the alternative hypothesis. This should be your alternative hypothesis, and it is. And it also confirms your mean and your standard deviation and sample size. So a really nice way to go. We will do more with the calculator. Really want to focus on that 5-step process. So let's go to the next example. In this next example, we've got M&M weights. A random sample of weights of 19. Let me grab my blue pen. So I'm just going to write down what I know here. This is for my sample. N is 19, sample. N is equal to 19. Sample has a mean of, so this is my sample mean, 0.8635 grams. Assume the population standard deviation. Now this case we're given sigma 0.0565. So we can use the normal curve. So we're going to use the z-test, the normal curve. We don't need degrees of freedom this time. Okay, so we're going to use a 0.10 significance level. This is my alpha, 0.10. Remember, this is the area of the rejection region. Area of the rejection region. To test the claim that the mean weight of all green M&Ms is equal to 0.8535. Okay, step number one. Step number one are the hypotheses. The null hypothesis is always the easiest. This is a test of the mean, so I start with mu, and the null is always equals. So it's going to be equal to, I do not want the sample mean, I want the hypothesized mean, this guy, 0.8535. For the alternative hypothesis, I need to decide if I'm going to use not equals, less than, or greater than. So it says, I don't just look to see if it's less than or greater than, I look to see if there's a claim that says they think it's less than or greater than. But really the claim is that the weight is. So I'm choosing this one. There's nothing here that says we think it's more, we think it's less. We can't base it on the sample value because that would be a bias. So instead we're going to say we didn't think it's more, we didn't think it's less, we just think it is. So if it isn't, then we use not equals, 0.8535. These two numbers are always the same. Because of that not equals, that means that I'm going to let my rejection region be either above that value, so here's my expected z-score of 0 with my expected mean of 0.8535. So I could be either significantly above or I could be significantly below. So I can shade in my rejection area here on either side. I have a rejection area size. My total size is 0.10, which means I really have 0.05 here and 0.05 here. So 90% of the time, these samples of 19 M&Ms are going to be close enough to 0.8535, but we're going to let another 10%, 5% above, 5% below, be significantly different then. So this is 90%. This is fail to reject, fail to reject my null hypothesis. And in these tails, this is a two-tail test, we're going to reject the null hypothesis. Reject the null hypothesis. Okay, you do not need all of that for part one. I just really like to set it up. I'm a very visual person. This right here, whoops, this right here is part one. Okay, step number two. Step number two is to find my critical value. This time I was given a population standard deviation. So these are going to be z's. I want my z critical value. I need to know that I've got a two-tail test to use my table. Two-tail test, and I have a significance level, that's my alpha, of 0.10. We're going to use table F. Okay, let's go over to table F here. So this time in table F, we've got two tails. Let me grab a different color. Yeah, sure, I'll do red. Okay, so I've got two tails, and it is 0.10, so I'm in the second column. But remember, all of the first values are t-scores. The z-scores are at the very bottom. So I'm just going to go to the very bottom here until I hit this value right here. So 1.645. You'll also see that it's 1.65. Either one is fine, plus or minus, because this is a two-tail test. Okay, so there we go. So it is, oops, I still have my red one, plus or minus 1.645. These are the z-scores that cut off that 90% region. So 1.645, positive 1.645. So I need to be 1.6 standard deviations away from my mean to say I'm significantly different. So that's what we've decided. Okay, so step number three. Step number three is to find our test value. So our test z. This is for the sample. I'm going to use my calculator this time. So I'm going to go to the step menu and over to tests. I do have statistics. I did choose the z-test, good. I'm assuming, let's see, this 0.8535. And notice how it's prompting you for a population standard deviation. So you have to have this population standard deviation. It'll let you throw any number in there, but make sure it truly is a population standard deviation. Okay, so 0.0565. My X bar is 0.8635. My sample size this time was 19. And there are my 3 choices for the alternative hypothesis. I'm going to hit not equals and then calculate. We're looking for that test Z, which is the second number in that list, and it is 0.77. It's positive. So if I put this on my normal curve, Z of 0.77 is going to land over here somewhere, 0.77. This lands in the fail to reject region. I want to also do this by hand. So if I were to do this by hand, I would take, it'd be the same formula. So X bar minus my mean, standard deviation happens to be a sigma this time, over the square root of n. So to calculate that guy by hand, so second quit, I go parentheses, point, my sample mean was 8635, minus my population mean 0.8535, 8535, divided by parentheses 0.0565, divided by the square root of my sample size, which was 19. So that averaged standard deviation. And we end up with that same value, a positive 0.77. So I get 0.77. So either way, doesn't matter, the calculator, or you can go ahead and do this by hand. Either way, I am not more than 1.6 standard deviations away. Instead, I'm only 0.77 standard deviations away. So that tells me that I am not significantly different. So my next step is my decision. Step number 4, this is either reject or fail to reject. This is another fail to reject the null hypothesis. And then the question, or answering the question. So I'd like to answer the question based on the claim. So we're testing the claim that the mean weight of all green M&Ms is equal to, we showed that we're in the close enough region. So we do support the claim. So we support the claim that the mean weight is about 0.8535. We weren't able to show that it was significantly different. So again, I've got those same 5 steps. Okay, getting better? Part D, the health of a bear population. Okay, so the health of a bear population in Yellowstone is monitored by periodic measurements. A sample of 54 bears, let's write this down, n is equal to 54 bears, reveals a mean weight, this is my sample mean, of 182.9. And a sample standard deviation. So this sample standard deviation tells me I need to use t-scores or a t-test. So a sample standard deviation, that's a big standard deviation, 121.8. At the 0.05 significance level, so alpha is equal to 0.05, that's the area in my tails or my significance regions. Test the claim, so here's my claim that the population mean of all such bears is greater than 150 pounds. Greater than, that sounds like a math symbol. So let's go ahead and go through our steps. Null hypothesis, tested the mean, always mu equals for the null hypothesis. We're not using our sample data, so we want to grab that 150. Alternative hypothesis, mu, I want to pick the right inequality based on the words I've got here. Greater than, so I want to know, is this greater than 150? So that's step 1. Step 2 is to find my test values. So I want to find my critical value, so my critical T, and I'm going to use table F, which means I need degrees of freedom. It's going to be 54 minus 1, which is 53. I've got a 0.05 significance level, and with greater than, let me just draw a really quick T-curve here. Here's my expected value of 150. Greater than, you can almost think of that as an arrow, right? It points to the rejection region. So this points to my rejection region on the right. This is going to be a one tail. Okay, so let's go ahead and put that into, or get the value out of our table. Table F, where'd it go? Okay, so here's table F. This time we want, grab some more colors here. That's what I get. I'll do a highlighter color this time. Okay, so this time we're doing one tail again. And we have, it was 0.05, right? So I've got 0.05. And I want 50, this time it was 53, wasn't it? But I'm not going to round up. So 53 this time is between 50 and 55. I don't round up. I'm conservative on these. I'm always going to take the lower value. So I'm going to take 50. 50, I'm in the second row, so I get 1.676. Go back, make sure that I actually got the right, yep, 0.05. Okay, so then I forgot, what was it? 1.676? Yep, 1.676. I'm on the positive side here, right? I didn't have my t-scores would be down below. So this would be positive 1.676. 1.676. That's what cuts off an area of 5% under my normal curve. I'm sorry, under my t-curve, which is pretty much my normal curve. Okay, so I've got my hypotheses. I've got my critical value. The next step is my test value. And I'm going to use the calculator to do this just because it's too easy, right? So step number 3, I want my test t. So I go over to stat and then tests. This time I want a t-test of the mean, so I want number 2. I do not have raw data, so I'm going to go ahead and keep it on statistics. My hypothesized mean is 150 this time. My sample mean, right, is 182.9. Sample standard deviation is 121.8. And my sample size is 54. Whoops. 54. Perfect. And I do want greater than this time. Another one-tail test. I calculate that to get that test t, and my test t is about 1.985. 1.985. If I put this onto my normal curve, it lands here, which is in my rejection region. So we reject if we're in the tail, and we fail to reject if we're not in the tail. So we end up rejecting this null hypothesis. So step number 4, reject the null hypothesis. Step number 5 is to state our summary. We're testing the claim that the population, so the claim is that the population is greater. This is my claim right here. So am I supporting the claim? Yeah, I did find a significantly higher weight. So yes, we support the claim. That the weight is higher. Then 150. Okay, so we haven't talked about could we be wrong though, right? So I've got a single sample here. 54 bears seems like a lot, right? When we have to anesthetize each of these and then somehow transport them at least far enough to get them weighed. So, I mean, that's a pretty big sample. But what about the time of year? So we have an expected mean of 150. But if we were weighing these bears close to hibernation time, we would expect that their weight would be higher than the expected weight of 150. So it's possible that there was a bias in our sample. We rejected the null hypothesis. Whenever we reject, but we think we did so because of some kind of not a math error, but some kind of a bias in our data. So some kind of a flaw. So whenever we reject and we think that there is some kind of a bias in our data, we say that there's a possible type 1 error. Possible type 1 error could also happen if maybe you just didn't have a big enough sample size. Maybe it's just a function of the sample that you happened to have. So again, maybe a lot of the bears that we weighed at this point were heading shortly into hibernation. So that's a possible type 1 error. If we go up to the last couple of examples, in the last 2 examples, we failed to reject. Whenever we fail to reject, but we think that there may have been some kind of a bias in our data, or we needed to collect more data, this leads us to, we call this a type 2 error. So this is a possible type 2 error. Type 2, do I have enough room? Type 2 error. Okay, what was this one? These were the M&Ms, weren't they? So we failed to reject, but we only took 19 M&Ms. M&Ms are not hard to weigh, right? So they could have been cracked, or they could have had a little more chocolate in them or something, right? That's a really small sample size. So I would say for this one, a possible type 2 error due to a small sample size. So could we be wrong? Could it really actually be 0.8535 is what we're saying? Or could it actually really be higher? Possible type 2 whenever we reject it. Okay, let's take a look at E. So in E, so we've got a real estate agent who believes that the average cost of a new home is $6,500 over the purchase price. She selects 40 home sales. Let's see, what color am I right now? Let's be blue. She selects, there we go, 40 home sales, so N is equal to 40. And finds that the average closing costs, so this is the closing costs, this would be of our sample, so this is X bar, is 6572. The standard deviation of the population, so this is going to be a z-test, 338, z-test. Alpha equals 0.05, test her belief. Okay, so step number 1, our hypotheses. This is a test of the mean, so we always start with mu equals for the null hypothesis. She believes that it is, the closing costs are $6,500, so $6,500. I stick with that number in the alternative hypothesis as well, 6,500. Average closing costs, it's more, but it doesn't say that she thinks it's more. She thinks it is, so it either is or it isn't. This leads me to a two-tail test. So I'm going to split that 0.05 into, I'll let this be significantly higher than or significantly lower than. So I've got a possible two-tail test here. Okay, so two-tail test. This is my expected value of $6,500. The question is, where does my 6572 live? We know it lives over here on the right, but does it live in the fail to reject region, the close enough to 6500 region, whoops, rejects, or does it live in one of our rejection regions? Okay, step number 2. Step number 2, we want the critical value. This time it's a critical Z value, 0.05 two-tail test. So let's go over to table F. 0.05 two tails. So now I'm going to be right here. So two tail 0.05. I'm going to go all the way down to the bottom of this third column. That's where my z-scores live, and I get 1.96. There are no plus or minuses in this table. I've got to put them in there. So I know it could be plus or minus because it's a two-tail test. Okay, so there's my critical z-scores. There are 2 of them. So plus or minus 1.96. Okay, so we've got plus or minus 1.96. We also need our test value, so we need our test z. I'm going to do that with the calculator. So I'm going to go to my stat menu, test, z-test, and I do have stats. My hypothesized mean is 6,500. My population standard deviation, and I do have it, is 338. 6572 is my sample mean. My sample size was 40. And I've got a two-tail test, yeah, so not equals there. And then calculate. Okay, so our test z is 1.347. So where does 1.347 fall? Remember, this was 1.96 and negative 1.96. So if I were to put this up on my normal curve, it would fall in the fail to reject region. So I would say number 4, whoops, I went blue, fail to reject. It's close enough, the null hypothesis, kind of what we would have guessed, right? 6572 doesn't seem that far off, especially with a pretty big standard deviation. Definitely less than 2 standard deviations away. So we fail to reject the null hypothesis. Number 6, we're testing her claim or her belief. So we do support her claim. So we support, I would write more, but I'm going to run out of room here. We support her claim. I'm just going to say the rest. That the average closing costs are $6,500. Okay, last but not least, oh, actually we have 2 more. So we'll do F. So a travel agent claims that the average number of rooms in hotels in a large city is 500. That sure sounds like a mu. Test at the 0.01 significance level. Is this claim realistic? Use the data below. So this time I've got data. N is equal to 1, 2, 3, 4, 5, 6, 7. N is equal to 7. I'm going to let my calculator, I'm going to do one variable stats. I'm going to let my calculator find the sample mean. And this is a sample. I can't just pull a population standard deviation out of the hat. This is certainly not the entire population of hotels. So if I have data, I can only use a sample standard deviation, which means I can only do with my sample data a t-test. So I'm going to go ahead and run a t-test. Step number 1, though, let's go ahead and start with the hypotheses. So step number 1, mu equals 500. And then the alternative, we're looking for less than, more than, just as is the claim realistic. So either is equal or it isn't equal. This is another two-tail test. I'm drawing a normal curve, but actually it's that t-curve. My expected mean is 500 with a t-score of 0. I'm going to start by putting my data into the calculator, and instead of, I could do one variable stats, but I can actually instead just do a t-test and tell my calculator that I have data in there, and it will do the rest. So we're going to do that. So I go to stat, and then edit. I'm going to go ahead and put these into L1, so I'm going to arrow up, clear, and then enter. And I'll go ahead and enter my data. So I've got 713, 300, 292, 311, 598, 401, and 618. Okay, and remember I said I had 7. Good, I've got 7 in my data set, so that's good. 618, 401, 598, 311, 292, 300, and 713. Good. Okay, that's the only thing I need to do different. Now I'm going to go into stats, tests. I was not given a population standard deviation, so I'm going to go to a t-test. This time, instead of stats, I'm going to click on data and enter to select it. My hypothesized number of rooms was 500. Just wants to know where my data is. It is an L1. I'm not using a frequency list, so I leave that at 1. And I've got a two-tail test. Great. So I go ahead and hit calculate. How nice is that? It does the rest of it for me. So I skipped step number 2, didn't I? So step number 3, this is my test t. So my test t is negative 0.57. Let's go ahead and find the critical t using table F. So for degrees of freedom, I have 6 degrees of freedom. I have this was a 2-tail test. 1 tail there, 1 tail there. So 6 degrees of freedom, 2-tail test, 0.01. So 2 tails, 0.01, 6 degrees of freedom puts me right here where my little cursor is, 3.7. It's a 2-tail test, so I know that I've got to do plus or minus. So this is plus or minus, it was 3 point something, right? 3.707? 3.707. Plus or minus 3.707. I definitely am not more than 3.7 standard deviations away. So I've got those plus or minus. This guy, it's a little bit less, but not much. I landed my fail to reject region. Step number 4, fail to reject. Possible type 2 error. Pretty small sample size, right? So we would definitely want a larger sample size on that one. Is the claim realistic? We do support the claim. Step number 5, we do support the claim. And the claim was that the mean number of rooms, was 500. Okay, now I think this is my last one. Woohoo! Okay, the average cell phone call length is reported to be 2.27 minutes. These are getting better, right, as we go. Reported to be, so this certainly sounds like our null hypothesis. Mu equals 2.27. A random sample of 20 phone calls. This is my sample data now. N is equal to 20. Shows an average, this is my x bar, of 2.98. Standard deviation, this is my sample standard deviation, 0.98. S, 0.98. So I do need a t-test here. Alpha is 0.05. Can it be concluded that the average differs from, God, I like that language. That tells me that I want a not equals in my alternative, not equal to 2.27. Okay, step number 2. I'm not going to skip it this time. I want my my critical t. So my t critical. I'm doing a t-test, aren't I? So that means I need degrees of freedom. So degrees of freedom, 20 minus 1 is 19. Alpha is 0.05, and this is a 2-tail test. My expected value has a t-score of 0. Okay, 19, 2-tail test, see if I can remember that, 0.05. 2-tail test, so I want this bottom row here, 0.05, 19 degrees of freedom. Oh good, it's on here. So 2.093. So 2.093, 0.05 2-tails, great. This is going to be plus or minus because I've got 2 tails. So plus or minus 2.093. So I've got to be just a little more than 2 standard deviations away. 2.093 below or above 0.93. So those are my 2, I want that guy. Okay, so those are my 2 rejection regions. So I've got my 2 rejection regions there. I'll reject if I am more than 2 standard deviations away, and I will fail to reject the null hypothesis if I'm not. Okay, step number 3. Let's let the calculator do it. Stat tests. This is a t-test of the mean. I do have stats this time, so I click over on stats. My hypothesized mean is 2.27. Average length of a cell phone call. Okay, so 2.27. My sample mean is 2.98. The standard deviation of the sample was 0.98. Sample size, we go back to the full N of 20. And this is a not equals, calculate. Okay, so we end up with a test T of 3.24. 3.24, let me grab the red pen, does live in my rejection region. It's more than 3 standard deviations away. That's where 2.98 lives. So 2.98 is more than 3 standard deviations away. This tells me that I am going to reject. So step number 4, I'm going to reject my null hypothesis. Step number 5, let me put it over here. Can it be concluded that the average differs from the population average? Yes, so it does. So yes, the average, and that would be our claim, is, and I'm going to put SIG for significantly, I'm just almost out of room, significantly different than the 2.98. Okay, now we did reject. So that means that there's a possible type 1 error. Whenever we reject, there's a possible type 1 error. And we want to think through why could that be. So we ended up with an average cell phone call of almost 3 minutes when the one that was reported was more like 2.5 minutes. So why would this be? So maybe we ended up interviewing people that were older who didn't text maybe as much as they called. We also have a really small sample size. That would be another reason to say, okay, we got a significant difference, but maybe it really isn't significant and we just need to sample some more people. So we can go back through, and anytime we rejected, there's a possibility of a type 1 error, but the possibility is really small. I was only ever going to reject in my rejection regions that only have a size of 0.05. So there's only a 5% chance or probability that we reject. So I've really minimized the probability of committing a type 1 error by making that tail such a small area underneath my curve. I can also go back every time I failed to reject. So this one, we didn't talk about it, but this one is a possible, not necessarily, but a possible type 2 error. So whenever you fail to reject, it's a possible type 2 error, and whenever you reject, it's a possible type 1 error. I hope those got easier. We're going to continue to use the same 5-step process. In some cases, we'll do the shorter 4-step process that we saw for the p-value tests as we continue in through all of our hypothesis testing.